Hi, my name is Neal Ford, and I'm with
VenkatSubramaniam.
And we're here to talk about concurrency in the modern world. The latest issue of the NFJS magazine featured articles about concurrency, and I wrote the intro to that kind of to contextualize this issue. And it's something that you can't really ignore as much as you have been ignoring it in the recent past for a couple of different reasons. One of which is based on an article that came out a few years ago by Herb Sutter, who's famous for writing about some of the early Windows programming stuff. And the title of the article is "The Free Lunch is Over." And you can Google that and you'll get his article, and he has a really compelling graph in it that shows that the real performance of machines has flattened out a long time ago. You can't keep making processors faster and faster because the smaller you make them, the closer the traces get to one another, and you get down to a point where the electrons start interfering with one another. As the dies get bigger and bigger, we're now to the point where dies are so big that it takes an electron more than one clock tick to make it from one edge of the die to the other, traveling at the speed of light. Those are some fundamental physics barriers that we're running into, and the way they solve that problem, of course, is not by making things smaller and smaller, but by adding multiple cores. So we're getting more and more cores in our processors now as a side effect of the things they've had to do to make processors efficient. Which means that you almost never execute code on a single core machine anymore. Which may seem okay, especially if you're like an enterprise developer. It's like, I let my application server handle all that messy threading stuff. I don't really care about that stuff. But the day is coming very soon where you're going to have to start thinking about that. Because we're starting to run into problems that require you to understand something about threading. Now let me give you the kind of classic parallel to this. 5 years ago, when you wrote a web application, you could write a really crummy web application and your users were still happy because it ran in a browser. It was kind of cool because you could get a browser-based application. And then Google came along with Gmail and Google Maps and showed our end users that web applications don't have to suck anymore. And that made us have to write non-sucky web applications and learn about AJAX and callbacks, greatly complicated our stack. We're starting to see classes of problems like social network graphs and real-time click analysis that require heavy scalability and heavy concurrency to solve those problems. And someone's going to come along and solve that problem really well, and it's going to be contingent upon you as a developer to be able to understand and deal with the multi-threaded implications of those kinds of problems.
Well said, Neil. Actually, that's a pretty important thing to keep in mind, that we are no longer in our father's environment anymore. On a single core processor, you didn't really have to worry too much. You had threads, but really they were multitasked. On a multi-core processor, the threading is on steroids. What really bothers me is when you look at an application, it may appear to be running correctly, but it's fundamentally broken when it comes to concurrency. I'm going to go out on a limb and say that probably 90% of applications out there are broken when it comes to concurrency. We just didn't know it. Well, the question is, how do we go about solving this particular problem? It's a problem that requires solution yesterday. We can't simply wait for it to take the time to solve it. We simply cannot afford to experiment on this anymore. We really need a solution. And thankfully, there are a few solutions out there for concurrency. The solution available in the Java platform, the JDK, I'm going to call it as synchronize and suffer model. It is something that is being tried out for a long time. And the real problem here is not that we are creating threads. The problem is we are spending way too much effort synchronizing it. And the problem is if we don't synchronize it or synchronize it at the wrong place, the result is quite unpredictable. And that's one of the things that really takes us to the path of where we can write code, but we don't know how correct the code is.
Which is a big problem, because those kind of problems don't manifest until you get under the heaviest load. They only show up in production when you've got a clustered environment, and they're almost impossible to reproduce. Those bugs can be really, really nasty to finally chase away from your process. Fortunately, we've got a lot of options in the Java world right now. There are some good options on the JDK, but there are also good options on alternative languages on the JVM that are much more suited to this exact problem. And I'm going to talk very briefly about Clojure, which is the Lisp on the JVM that has a lot of really sophisticated features in it that make concurrent programming much safer from a developer standpoint. It's not the synchronize and suffer mode anymore. Clojure, being a functional language, has specific mechanisms in the language to make it easy for you to do safe updates to state without having to worry about synchronization and all that other stuff, because it happens at the language level. In fact, Clojure has a very sophisticated software transactional memory system where you can do transactional processing in memory and make sure that you make atomic changes across multiple things, and the language guarantees that that happens correctly. So you don't have to worry about locking and blocks and all that stuff anymore, which greatly simplifies your development. But of course, to do that, you have to move to a different language.
Which is, the next point I want to bring up here is, that's the real fun, I think, is I think the model that Clojure brought up is fundamentally phenomenal. And the reason for that is Richie brilliantly brought together a separation of the state from the identity. Now, it's really nice to be able to move into it, but it turns out, if you really look at Clojure itself, the do-sync, which is what we are using to call into transaction, is a syntax sugarcoating in Clojure, which really is nothing but a run-in transaction method in Java. And similarly, the ref keyword that you use in Clojure to create a managed reference is actually exposed underlying as a ref object in Java. So it turns out there's two things on hand. One is you can actually use the Clojure's model directly from real Java code. You could basically wrap your code that wants to be in a transaction into a run-in transaction. And this couldn't be simpler, because the only thing run-in transaction requires from you is just a callable object. So just go ahead and create a Clojure lang ref object, and if you modify it anywhere outside your transaction, you get a slap in your wrist telling you that you're not supposed to modify this because you're not in a transaction. So this goes back to my earlier comment where the unpredictability in the synchronize and suffer is completely removed from your shoulders. You get a clear deterministic error that you violated the transaction model. And when you call it from the run-in transaction mode, the code you put in there runs within a transaction, and just like how the do-sync in Clojure rolls it back when there's a violation of transaction boundaries, that's exactly what happens. Now, then what's the reason to really use Clojure? The fundamental difference is in Clojure, state is immutable, period. So if you're going to use this from Java, the onus is on you to ensure that you don't modify the state, whereas you can almost code in sleep when it comes to Clojure and get a better comfort with concurrency. But if you do have to program it in Java, you can still use it, but you have to be awake and pay attention to make sure that your state really is immutable and only the identity is immutable.
Well, and that brings up an interesting point in that functional languages really like immutable data structures. And in fact, Michael Feathers had a great quote that said imperative languages like Java and Ruby and Groovy try to make managing state easier. Functional languages try to make you not have to manage as much state, immutable state. And that is one of the really great things that functional languages like Scala and Clojure have taught us, is that immutability has numerous benefits, including much more elegant interaction with threading and concurrency. And so you can get a lot of these benefits in Java, like Venkat said, if you start using more immutable data structures. When you build code, even in Java, think about, does this really need to be mutable, or can some of it be immutable, and stop using the default in Java, which is everything is mutable, and start thinking more about mutability. Because ultimately, no matter what language you write this in, immutability is going to be your serious friend when it comes time to do serious concurrency.
So that brings up the question, okay, great, we could either move to use Clojure, or we could go ahead and use the Clojure STM API from within Java, or we could reach out to other implementations like Multiverse. But while that's a very interesting solution, the world as it is pretty interesting because everything has its limits. So software transaction memory, as beautiful and wonderful it is, does have some limitations as well. And so one of the things that I observe is that while you can pretty much not worry about synchronization issues anymore, I find that STM is very useful when the write collisions are infrequent. Now, this is not about the frequency of writes itself, but more so the frequency of write collisions. You could, for example, let's say you're on a typical web application, multiple requests come in, each of the requests modify data, STM is just fine for it, because these are frequent writes, but there's no write collision. Pretty much each user is kind of independent of the other users. But in applications where the writes do collide and want to compete for the same shared data, STM is going to fail miserably. And the reason for that, of course, is that the transactions are going to get repeated quite often, and you simply cannot sustain that kind of conflict. And that's why I think there is fortunately a third option available on hand, and we should talk about that, I think, which is the actor-based concurrency model.
Yep, which is very popular, popularized in Erlang, but now very evident in the Scala world, which is a different model for doing that kind of concurrent development, which are more autonomous interactions between things, not in the software transactional memory, but much more independent kind of actors in your concurrent situations.
And so actors are pretty useful. A lot of times, this is something that I was laughing at this as I was gaining knowledge and learning through this. Is back in school, you probably remember, Neil, that we studied about active objects, where objects kind of run in their own threads, and then object-oriented programming kind of came along and took us in a different direction. Mm-hmm. But what's really funny about actors is that actors are really active objects. An actor is quite fundamentally different from an object in that an object encapsulates data, but you pretty much can call these methods from any threads and get into the mess of synchronization. Whereas an actor says, hey, I am single-threaded. I know this is probably not a popular thing to say, but reminds me of STM, of STA, the software, the COM model, the single-threaded apartment model.
I was about to say the apartment threading model is exactly what that is.
I don't think we're going to make friends saying that a lot, but
if you don't know what the apartment threading model is, don't go look it up. You don't want to find out what the apartment threading model was. Trust us on this.
But essentially, that's what you're looking at is a single-threaded model, and you're saying, I'm an object, you can call any method on me, but I'm going to run it in one single thread. Well, guess what? We fundamentally removed the concern of shared mutability, and I want to define the word isolated mutability for that. So yes, I am favoring mutability still, but I've isolated that completely from the outside world, not just in terms of encapsulation, but in terms of saying, hey, only one thread ever executes this. Mm-hmm. So we eliminate a lot of these synchronization problems that way. And so even if you have a heavy contention for writing, you're not going to get into a failure state. All that you're going to do is compromise on performance, because you're going to end up queuing to get through this. Yeah. And so that is certainly a different model to consider as well.
Well, and this just brings up the point that this is still a complicated problem. The tools are getting much more sophisticated for this, languages are adding support for this, but this is still a pretty complicated thing, and it's something that almost nobody gets right. And because it's so complicated, it's very error prone, and it's hard to do correctly, and you have to think. There is no one-size-fits-all solution. Whether in a language or framework or any kind of tool, you have to apply intelligence to this problem and think about what are the characteristics that I need for this concurrent application, and what are the best kinds of tools and techniques that I can overlay on this to get the best return on investment for my time and effort in doing this, and the best bang for the buck for getting this problem done.
I think that the beauty of this is we had a very tough problem and an inadequate set of tools. Things have improved to the point where we still have a complicated problem, but at least our hopes are raised right now. Yeah. We got some reasonable solutions on hand, and it's for us to raise our skills to be able to use some of those options. But with the proper tool on our hand, I think we can still solve this problem now than any time before.
We're both cautiously optimistic.
Let's put it that way. Thank you.
Thank you.